Hey everyone, and welcome. Today, we are going on a serious journey. We're going to build our understanding of the universe from the ground up, literally block by block, to see how everything, and I mean everything, actually works.
So, let's just dive right in with something you've all felt before. You're on a bus, it's moving along, and then bam, the driver slams on the brakes. You feel your whole body get thrown forward, right? Well, why does that happen? The answer to that simple, everyday question is our very first building block for understanding all of physics. And the answer is one simple but incredibly powerful word: inertia. It's this core idea that things like to keep doing whatever they're already doing. If something is sitting still, it wants to stay still. And if it's moving, like you are on that bus, it wants to keep on moving. The brakes stop the bus, but your own inertia is what keeps you going for that split second. This is our starting point.
So, here's our game plan. We're going to start with the foundation, why things move in the first place. Then, we'll look at the engine that powers it all, energy and work. After that, we'll get into the invisible forces shaping our world, find the spark that ignited modern life, and finally zoom all the way out to see the universe's grand design.
All right, let's get into it. First up, the foundation. Before we can understand anything else, we have to nail down the absolute basics of why stuff moves or doesn't move. And for that, we look to the one and only Sir Isaac Newton and his three famous laws of motion.
And just like that, we're back where we started. Newton's first law is really just the official name for inertia. Your body, zipping along at the same speed as the bus, wants to keep zipping along at that speed. The bus brakes are an outside force that acts on the bus, but not directly on you. And that's why you lurch forward. Simple as that.
Next up, we've got what might be the most famous equation in all of classical physics: F equals m. It's just three little letters, but they unlock the entire relationship between force, mass, and acceleration. It is so simple, so elegant, and it explains so much.
So what does it actually mean? Well, F is for force, any kind of push or pull. M is for mass, which is basically how much stuff an object is made of. And A is for acceleration, how fast that object's speed changes. This little formula tells us exactly how those three things are connected.
And here's where you see it in the real world. Imagine you give the same exact powerful push, the same force, to both a bicycle and a giant loaded truck. The bicycle, with its tiny mass, is going to take off. It's going to have a really high acceleration. But that same push on the massive truck, it'll barely move. It'll have a very low acceleration. The more mass something has, the more force you need to get it moving.
And Newton's third and final law is one you've definitely heard before. For every action, there is an equal and opposite reaction. A swimmer is the perfect example. The action is them pushing the water backward with their hands. And the reaction? The water pushes them forward with the exact same amount of force. It's just how the universe works. Okay, so we've got the rules for how things move. But what actually gives them the juice to move in the first place? What's the fuel in the tank? Let's get into our next section and talk about the engine behind it all, energy and work. So when you get right down to it, mechanical energy comes in two main flavors. First, you've got potential energy. That's stored energy. Think of a roller coaster car, click-clack clicking its way to the very top of the highest hill. It's just sitting there, loaded with potential. Then you have kinetic energy, which is the energy of actual motion. The moment that roller coaster tips over the edge, all that stored potential energy converts into pure, thrilling, high-speed kinetic energy. Now, this is where physics can be a little tricky. In everyday life, work means effort, but in physics, it has a very specific definition. Work is only done when a force actually makes something move a certain distance. So, pushing a lawnmower across the yard, that's work. But what about holding a super heavy bag of groceries perfectly still? Your muscles are screaming, you're sweating, but in the eyes of physics, because the bag isn't moving, no work is actually being done on it. Crazy, right? And if work is about getting something done, power is all about how fast you do it. Let's say a sprinter and a walker both have to pull a weighted sled for 50 feet. They both do the exact same amount of work in the end, but the sprinter, who does it in just a few seconds, is generating way more power. Power is simply work divided by time. So we've covered the direct pushes and pulls and the energy that makes them happen. But now let's talk about the invisible forces that are constantly shaping our reality every single second of every day: gravity and friction. Okay, this is one of my favorite facts in all of science. We all instinctively think that heavier things fall faster, right? But that's just because of air resistance here on Earth. If you take away the air, like in a vacuum, or, say, on the moon, gravity pulls on everything at the exact same rate. And this was proven in the most beautiful way during the Apollo 15 mission, when an astronaut dropped a hammer and a feather, and they fell side by side, hitting the lunar surface at the exact same moment. And then there's the other big unseen force, friction. And it's kind of a double-edged sword. You've got static friction, which is the good kind. It's the grip that keeps your shoes planted on the floor so you don't slip. And then there's kinetic friction, which is the force that slows things down, like when a car's tires screech on the road to come to a stop. All right, from the forces keeping us on the ground, let's switch gears to the unseen forces that power, well, pretty much everything in our modern world. It's time to talk about the incredible link between electricity and magnetism. The whole thing starts with electric charges, and the rules are actually really simple. You've got two kinds, positive and negative. Opposites attract and likes repel. And you know that annoying static cling you get in your laundry, where a sock just refuses to let go of your shirt? That's it. That's this fundamental force of the universe in action, right in your laundry basket. Now, Ohm's law is what runs almost all of your electronics. The I stands for current. That's the flow of electricity. V is voltage. You can think of that as the electrical pressure pushing the current along. And R is resistance, which slows the current down. Your phone charger is a perfect example. It uses voltage to push the current through the resistance of the wire to safely fill up your battery. Getting that balance right is everything. And this is where things get truly mind-blowing. It turns out that electricity and magnetism are really just two sides of the same coin. A moving electric charge creates a magnetic field, and a moving magnetic field creates an electric current. This amazing relationship is what runs our world. It's how giant electromagnets can lift entire cars, and it's how we spin turbines and dams to generate the power that lights up our cities.
Okay, buckle up. We've built our way up from basic motion to energy to electromagnetism. For this last part, we are zooming way, way out to the biggest scales imaginable, and then zooming way, way in to the smallest, to get a peek at the universe's truly grand design. Albert Einstein didn't just tweak the rules, he rewrote the entire rulebook. He showed us that mass is just a super concentrated form of energy with his famous equation E equals mc squared. He also showed that space and time are woven together into a single fabric called space-time. And get this, time itself can actually slow down. This isn't just a sci-fi idea. The GPS satellites orbiting the Earth are moving so fast that their clocks literally run slower than ours. Engineers have to constantly correct for this time dilation, just so the map on your phone can give you the right directions. And if you thought that was weird, well, when we zoom all the way down to the level of atoms, things get even stranger. Welcome to quantum mechanics. Down here, particles can act like waves. They can be in multiple places at once. We can never know both where a particle is and where it's going with total certainty. It sounds like absolute nonsense, I know, but harnessing this quantum weirdness is exactly how things like solar panels and the flash drive in your computer are even possible. So there you have it. We went from a simple lurch on a bus all the way to the fabric of space-time and the bizarre dance of quantum particles. Each discovery was a new block, placed carefully on the one that came before it, building this incredible picture of how our universe works. And that journey is far from over, which leaves us with the most exciting question of all. What's the next block going to be?